Suppose there are 1,000 MNU students and their heights are normally distributed with a mean of 68 and a standard deviation of 3. We're going to simulate this, and I've left the instructions here if you want to go back and look at the instructions later and try it on your own. But we're going to do a simulation. Probability simulations on a computer are really important in practice whenever the math behind combining probability distributions in different ways gets to be too complicated. And instead, you just want to sort of generate random things and see how it plays out. Those are called Monte Carlo simulations. You might hear that in like business classes later on. That's basically just using random variables that are simulated like this to come up with a distribution of possible outcomes. And then you can use inference like confidence intervals and hypothesis tests on the simulated data rather than using math. I mean, I guess it's still math, but it's one math or another. You pick your poison. What are we doing? I'm going to use the normal distribution quantile function with a random number between 0 and 1. And I'm going to tell it to use a mean of 68 and a standard deviation of 3, so that every time it runs this formula, it's making a random height of a student. Like this randomly selected student has height 70.8 inches. And then I'm going to do this 1,000 times to simulate having 1,000 students on campus. So you can see the row number. I just made 1,000 students and their simulated heights. I'm going to copy and paste this as values so that the formula goes away. I just don't want this to recalculate every time. I want to have a set number of like, 1,000 students here in column A. Okay, the next thing I'm going to do is I'm going to generate random numbers between 1 and 1,000. So that cell formula is going to give me an index of a random student, student number 1 through student number 1,000. And this is a way that I can generate a random sample. I can randomly select student number 842 or 22, right, as I generate random numbers. And I know that there's already a row number here, but I need to actually tell Excel in column A to index the students by row. So I'm going to type in equals row with little parentheses there, and that's going to tell me the row number. And this is a little bit silly, but if I double click on the bottom right corner, it's going to fill in all of the row numbers. Okay, so back to this. I want to take a sample of 30 students. So I'm going to make sure that I get 30 of these. That's 16. That's 35. Let me see if that's 30. Okay, perfect. So this is 30 random numbers between 1 and 1,000. And then the next thing I'm going to do in my simulation is I'm going to look up. Let me zoom in closer so you can see the formula I'm using. Okay, I'm going to look up this student with number 212 out of the array that sits in columns A and B, so it's the red shaded region there. I'm going to hit F4 one time so it locks that region in place. I'm going to put a comma. The next thing it asks me is for the column index number. That would be 2 because I'm looking at the heights that are in the second column of the red table. And then the last thing I need to do is type in comma false because I want an exact match for the index. Now, this is telling me if I go down in my table and I look for student number 926, that student's going to have a height of 65 inches, right? So this is how I can quickly pick out students from my group of 1,000 and then find student number 894, and he's going to have a height of 66.5, right? And again, I want 30 students in my sample. So I pull this over, and I've got 30 measurements. And then the last thing I want to do is I want to take a sample mean. And so the sample mean in Microsoft Excel is going to be equals average, like that. And then I select the numbers that I want to average. So I'm averaging those 30 numbers, and boom. So column C is going to have the sample means of height. Whenever I randomly select 30 of those 1,000 students and I calculate their sample mean. So I'm going to make this a little bit more compact. I'm going to steal the rand between and put it here. And then now I don't need the first row. You're going to see why I'm doing this in a second. Because now I want every single row of this spreadsheet to contain a different sample of 30 random students. And then we're going to take the sample mean here in column C. And now I just need to, oops, that's not what I wanted. Okay. This is kind of annoying. What am I trying to do? I'm trying to fill down this formula. Maybe the easiest way is I select it and I'm going to double click on the right corner, bottom right corner here. There we go. That does it. So now there's 1,000 rows in this spreadsheet that are filled up with samples of 30 students, and I put the sample means in column C. Column B, remember, is like individual students' heights, okay? Column C is what I get if I sample 30 students at random and then I take the mean of 30 students' heights. So B is my underlying distribution of measurements. And there's a little histogram for my students and their heights from column B. Column C is going to be the sampling distribution of the sample mean. If you can't read this very well, then I invite you to, to take one of these empty seats in the front row, because the numbers get a little bit small to read here. But on the left, this histogram has measurements of students. And some students are really tall. Like there's at least one student who's between 77 and 78 inches, right? Some students are really short. There's at least one student that's between 60 and 61 inches. Most of the students are around 68 inches because that's the mean of the distribution. And it's symmetric, so obviously like the highest probabilities are near the middle. What is this over here? This is the distribution of the sample means. Whenever I take 30 students at random, I calculate their average. This is that distribution. It looks kind of the same. It's symmetric. It's a normal distribution. The difference, you can only really tell the difference if you look closely at these numbers. The smallest numbers over here are only like 66. And the largest numbers over here are only like 69. So like the entire dispersion of this distribution is about 3 inches from like minimum to maximum. Over here, this lowest number is 60 and this one is 77. So the entire dispersion of this distribution is over the course of like 17 inches. This distribution has a whole lot more dispersion than this one. They both have the same mean, around 68. They both have the same shape, but just the dispersion is way less when I look at the distribution of sample means. And it should make sense, right? Like if I sample 30 students at random and average that together, we expect the average to be pretty close to the center. Even if there's some super tall students in the sample and some really short students in the sample, they kind of cancel each other out. So this is the big idea for today. This is what we call the central limit theorem. If the underlying distribution of measurements is a normal distribution, then the distribution of the sample mean will be a normal distribution. If the underlying distribution is not normal, then the distribution of the sample mean is not necessarily normal. But if I have a large enough sample size, then we still say that the normal distribution is an adequate model for the distribution of the sample mean. In other words, if the underlying distribution is not normal, then the distribution of the sample mean is still approximately normal, provided that the sample size is at least 30. That's usually our heuristic. Our rule of thumb is that we want a sample size of at least 30. Because if you have a small sample size and you have a distribution that's not normal, not symmetric, then you could honestly have a distribution of the sample mean that's not normal. But if your sample size is large enough, it doesn't matter what the underlying distribution is. Maybe your underlying distribution is like an exponential distribution. Okay, fine. But if you've got a large enough sample size, the sample means will still be approximately normal. So this approximation gets better and better as the sample size gets larger. And so if your sample size is like 1,000, then that's great. That's even closer to the normal distribution. The mean of the distribution of the sample mean, which is this symbol right here, that's mu for mean, and then x bar represents the sample mean. Remember, the mean is a parameter. The sample mean is a statistic. And it's also a random variable in this case. So this symbol would be the mean of the distribution of the sample mean. And that's just going to be equal to the mean of the underlying distribution. Over here, this sigma with the subscript x bar, that's the standard deviation of the distribution of the sample mean. And that's going to be equal to the standard deviation of the underlying distribution divided by the square root of the sample size. So that means as n, the sample size, becomes larger, then the distribution of the sample mean is going to shrink. If I have a really big sample size, then my distribution of the sample mean is going to be very, 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 very precise. There's not going to be much dispersion. In red, you can see a little bell curve. You can see the normal distribution probability density curve in red for a distribution with mean 68 and standard deviation 3. That's what that red curve represents. The blue curve is what it would look like to distribute the sample mean. It's still a probability distribution. The mean is still at 68 inches, but notice how much more precise it is. There's way less dispersion in the blue curve because we're dividing the standard deviation by the square root of 30. So the standard deviation becomes a lot smaller. Everything else about it is the same. Any questions so far?
Wait, so the smallest red is what again?
In red, this curve has a mean of 68 and a standard deviation of 3. the blue curve here has the same mean, but the standard deviation of the distribution of the sample mean is going to be the standard deviation divided by the square root of the sample size. So that would be 3 divided by the square root of 30. And so that would be only a standard deviation of 0.5477. So these curves have the same mean, but the blue curve has a much smaller standard deviation because I've got a pretty decent sample size. Okay. Exercise 2 says IQ is normally distributed with mean 100 and standard deviation 15. You select 10 individuals at random and test their IQ. What's the distribution of the sample mean? Well, since IQ is normally distributed, my underlying distribution is normal. It's normal with mean 100 and standard deviation 15. Then the distribution of my sample mean is also going to be normal with a mean of the same 100 and a standard deviation of, well, I have to use the formula. And my formula says the standard deviation for the distribution of the sample mean is the standard deviation of the underlying distribution, which is 15 in this case, divided by the square root of the sample size. In this case, the sample size is 10. So I divide by the square root of 10. And this standard deviation is then going to be 4.743. You got to use this formula. This says you take the standard deviation, which is 15, and then divide by the square root of n. N is your sample size, and my sample size is 10 in this problem.
So is that just the answer to the first bullet point?
Mm-hmm.
Okay.
For the second bullet point, everything is exactly the same, meaning it's a normal distribution with mean 100, but the difference is that n is now equal to 20. So I have to update my standard deviation of the sample mean. And so my standard deviation of the sample mean is now going to be 15 divided by the square root of 20. Again, using that formula. What if I have a sample size of 40 individuals? That would be the same but n equals 40. So the standard deviation of the sample mean would be 15 divided by the square root of 40. The shape stays the same. Since the underlying distribution is normal, then the distribution of the sample mean will be normal. So the shape doesn't change when you choose a different sample size. The mean doesn't change. The mean of the distribution of the sample mean is always going to be 100 because that's the mean of my underlying distribution. The mean stays the same. The only thing that changes as I increase my sample size is that my standard deviation is going to shrink, and it's going to shrink according to this formula. You just have to update your standard deviation using that formula. Any other questions? Okay, we'll do a couple more examples. In a football punting contest, among MNU students, the punt distance in yards is exponentially distributed with a mean of 20 and a standard deviation of 20. You randomly select 10 individuals and measure their punt distance. What is the distribution of the sample mean? N equals 10. That's less than 30. So the sample mean is not normally distributed. I'll scroll up and I'll remind you of what we said earlier. As part of the central limit theorem, we said if the underlying distribution is not normal, then the distribution of the sample mean is still normal, provided that n is greater than or equal to 30. If n is not greater than or equal to 30, we can't do anything. We just say, oh, well, that sucks. The sample is too small. We're not going to do any inference with it. What's the next bullet point say? What is the distribution if we randomly select 30?
Wait, the last one was 10, but it was normal.
It's because it was normal.
Because it was normal. Yeah.
Wait.
Let me scroll up again. It says, if the underlying distribution of the measurements is normal, then the distribution of the sample mean is normal. And there's no lower threshold for sample size.
Oh, it says.
I thought the same exact thing. I was like, well, I'm screwed.
Okay, sorry.
Okay. So if n is equal to 30, then in this case, the sample mean is approximately normally distributed. Of course, it's not exactly normally distributed, but it's good enough, right? These are all heuristics. The word heuristic means it's a rule of thumb. Like, we just are choosing n equals 30 as our threshold. Why? Because that's the convention. Obviously, this gets better if n is larger, and it gets worse if n is smaller. So you've got to choose. You've got to choose some point to cut this off, right? We could have said n equals 29 or n equals 31, but we decided n equals 30 sounds like a nice number. You know, it's a heuristic. So we say, in this case, since n equals 30, this is approximately normally distributed. So we say that the mean of the sample mean is going to be the mean of the underlying distribution, which is 20, and the standard deviation of the sample mean is the standard deviation of the underlying distribution divided by the square root of n, the sample size. So that'll be 20 divided by square root of 30, which is 3.651. Questions? Yep. Last example today. A random number generator on your computer uses the uniform distribution with a equals 0 and b equals 1 to generate random numbers. If you generate 10 random numbers, what's the distribution of the sample mean? And this underlying distribution is not normal. It's a uniform distribution. So the sample mean is not normally distributed.
Wait, on the test, would you want us to find the mean of the uniform distribution, or are we done doing that?
The mean of the uniform is pretty easy. It's the midpoint between A and B.
So it's just 0.
It'd be 0.5. Yeah. The next bullet point says, what happens now if we generate 100 random numbers? What's the distribution of the sample mean? So in this bullet point, n is equal to 100. So n is greater than 30. So the sample mean is normally distributed. With a mean of the standard deviation, the mean of the the mean of the distribution of the sample mean. There's so many words in statistics. The mean of the distribution of the sample mean is the same as the mean of the underlying distribution, which in this case is 0.5. And then we need the standard deviation of the distribution of the sample mean, which is going to be the standard deviation of the underlying distribution divided by the square root of n. And the square root of n will be the square root of 100, which is just 10. What about the standard deviation of the uniform distribution? This is a formula that I think at one point you probably wrote down on your 8.5 by 11 page of handwritten notes on the last test. It's something like 1 over 12, I want to say.
Isn't it it's like the top, the inbound minus, or something like that?
Is it that?
I don't know.
So obviously, you can put the standard deviation formulas on your note sheet. I'm just going to try to double check my memory here, make sure I'm not remembering this wrong. But if I want Wikipedia continuous uniform distribution, let's see what it says the variance is. Okay, so I just remembered the variance formula. How is standard deviation related to variance? So I just need to take the square root of this. B is 1 and A is 0. One minus 0 is 1. 1 squared is still 1. So I need to take the square root of 1/12. And that's 0.2887.
So how do we know that it's not discrete uniform? Is that because you can't get a discrete number between 0 and 1?
You're right. Yeah. I should have said continuous uniform to be more specific, but it's true that, I don't know. If it was a discrete uniform, your only possible outcomes would be 0 or 1, right? So I really should be more careful. I should say continuous uniform. You're right. Okay. So now I've got 0.2887 as the standard deviation for my underlying distribution. Now when I want the distribution for my sample mean with 100 random numbers that I'm averaging together, this is going to be 0.02887. Early in the semester, we were calculating z-scores. And the z-score of a measurement was like taking a particular measurement minus the mean of that distribution and dividing by the standard deviation. Remember, this was like, I think section like 1.4, so like way, way, way back when we were getting ready for the first test. We would have like, I don't know, a javelin thrower, and we know like what the population mean javelin throw distance is and the standard deviation, and we would say, yeah, we can calculate the z-score of any particular throw, and then we could use the z-score to create a percentile by using the standard normal CDF. And then the percentile would tell us, oh yeah, you're like the 90th percentile javelin thrower, or the 99th percentile javelin thrower. That's what we were doing with z-scores earlier in the semester. But on Friday, we were talking about the distribution of the sample mean as a random variable. And the distribution of the sample mean as a random variable was the same if it was a normal distribution. But what was different is that the sample mean has a smaller distribution standard deviation. It's the same as the underlying distribution standard deviation, but divided by the square root of the sample size. Because the larger the sample size, the smaller the dispersion on the distribution of your sample mean. In other words, we expect your sample mean to be more accurate if you have a larger sample size. And this would be standard normal distributed, right? We would plug the z-scores into a standard normal distribution to get our percentiles. And now the question is, how would the distribution change if we do not actually know the exact value of that standard deviation. Because in real life, we don't know what the mean of the underlying distribution is. We don't really know what the standard deviation of that distribution is. Whenever we approximate the standard deviation with this lowercase s sample standard deviation, we are introducing some uncertainty. And the resulting distribution is called a t-distribution. And so you might call these like t-scores instead of z-scores. Because we are approximating with the sample standard deviation. And the t-distribution is a lot like the standard normal distribution. Here in blue, you can see the standard normal curve. In orange, you can see a t-distribution curve. But we say it has heavier tails. That means there's more probability for the extreme values out here. Do you see how there's more? The orange curve is on top. See how the orange curve is larger than the blue curve when you're really far to the left or really far to the right. So that's what we mean by heavier tails. But it's still symmetric. It's still bell-shaped. It still looks like the normal distribution, just heavier tails. More probabilities at the extremes because we're creating more dispersion in our distribution. When the sample size gets really large, the t-distribution approaches the normal distribution. And this is one thing we looked at on Friday, I think. This is what it looks like if I have a sample size of 2. But if I increase the sample size, then my t-distribution gets closer and closer to the normal distribution. So when my sample size is 30, or 31, it's not exactly the same as the normal distribution, but it's really, really close. If I make my sample size 3,000, then it's almost indistinguishable. And that's because if I have a really, really large sample size, then I expect my sample standard deviation to be a really, really accurate approximation of my distribution standard deviation. So there's really less uncertainty here. And of course, whenever I have a small sample size, like 15, well, that introduces more uncertainty because with a sample size of 15, I can't really get a good approximation of my population standard deviation. And so lower sizes of samples are going to have more deviation with that t-distribution. Okay, so when we say degrees of freedom, it's a new vocabulary word. The degrees of freedom of the t-distribution is n minus 1. It's 1 less than the sample size. So if I have a sample size of 30, my degrees of freedom is 29. So let me show you a question I could ask you about t-distribution. It says beef cattle are typically turned into meat at 18 months of age. Suppose that these 18-month-old cattle have weights that are normally distributed with a mean of 1,300 pounds and a standard deviation of 75 pounds. We randomly select a sample of 20 cattle from this population and calculate their mean weight to be 1,340 and their sample standard deviation to be 71. What is the z-score and percentile of their sample mean? So the z-score of the sample mean is going to be the sample mean minus the population mean divided by the standard deviation of the distribution of the sample mean. So in other words, that's going to be x bar minus mu over sigma divided by square root of n, which is going to be 1340 minus 1300 divided by 75 divided by 20, square root of 20. Okay, so be very careful about how you put that in. I would obviously use parentheses in the denominator so that we get open parentheses 1340 minus 1300 divided by open parentheses 70 divided by square root of 20, close parentheses, enter. I get 2.385. That's the z-score. If I want to get the percentile, then I need to look at my normal distribution and calculate the area that's to the left of 2.385. 2.385. So Desmos can tell me that the area to the left of 2.385, the shaded region, is going to be an area of 0.9915. If you don't have Desmos, you can look it up on the table. Just like we did at the beginning of the year, section like 1.4. It's kind of a review. I guess the only thing different from what we did in section 1.4 now is that we are having to calculate the standard deviation of the distribution of the sample mean instead.
So will we ever use, do we just need to know the equation to the right? The one that has yeah, we just need to know that one.
Yeah.
We would never use the other one.
I mean, it's the same thing.
Okay.
Yeah, it's exactly the same thing because whenever I have the little subscript, x bar subscript, this is the standard deviation of the distribution of the sample mean. This sigma without the little subscript is the standard deviation of the underlying distribution of weights because they're not the same distribution. I had a picture on Friday. I'll see if I can find it. That showed the difference here. So imagine the red curve is like the weight of these cattle, right? Every cow belongs to this red distribution of weight. Well, the samples, once I collect a random sample of 20 cows and I weigh them and then I calculate the sample mean, that sample mean is a random variable because it'll change every time I get a new sample. But the distribution of those sample means is like this blue curve here. All the probability is more tightly squeezed around the mean. So it has a smaller standard deviation. And how small is it? Well, it's exactly this. It's the underlying distribution standard deviation divided by the square root of the sample size. So the larger the sample size, the smaller the standard deviation of the distribution of the sample mean. Yeah?
I'm sorry, how did you get 99.15, like, without using Desmos?
Oh, without using Desmos?
Is it just look at the charts that we have?
Yep, you got to look at those charts.
Is the t distribution multiplication or just the normal z-score?
Right now, we're just doing the z-score. So for the z-score, you use the standard normal distribution CDF. And we get out this highlighter and we say, .385 or something like that.
Yeah, that's right.
There's 2.3. And I guess 8.5 would round to 9. So we're looking at, on the table, it's 0.9916. So if I looked up this table value, it would be 0.9916 from the table. And that's only a tiny deviation from my Desmos answer, which was 9915. Yep. All right, it says, now suppose we don't know the actual value of sigma. What's the t-score and percentile we calculate for their sample mean then? So again, pretend we don't know the actual value of sigma, okay? This means pretend we do not know that sigma equals 75. What would we do instead? We would calculate a t-score which is the sample mean minus the distribution mean divided by the standard error of the mean. In other words, the lowercase s is like, it's kind of like the sample standard deviation of the sample mean.
Is it sometimes SE for?
Yeah, sometimes it's written SE for standard error.
So what happens? So like, is it okay if we write that instead?
Yeah, that's fine.
That's fine.
But this would be x bar minus mu divided by s divided by square root of n. Again, because this standard error is going to be approximated by taking the sample standard deviation and dividing by square root of n. That's what's happening here. And then once again, we're going to have 1340 minus 1300 divided by 71 divided by square root of 20. So again, be super careful about how you put this in your calculator. I would put parentheses in the numerator, parentheses in the denominator. See what we get. So I got a t-score of 2.52.
That should be 71.
71 is in the problem right here. But these t-scores do not follow the standard normal distribution. They follow a t-distribution. The t-distribution is kind of crappy. I'll explain why. It's kind of a headache for both students and teachers alike, and I'll try to explain why. Here's my t-distribution. And I want all of the area to the left of the point 2.52. And this depends on the sample size. Our sample size is 20. Let me fix my little Desmos real quick. Okay, I guess I can't fix it. Okay. So here's my t-distribution with sample size 20. And the area that's to the left of 2.52 is 0.9896. or in other words, 98.96% from using Desmos. That's pretty close. That's pretty close to the percentile we got earlier using the z-score. And again, that's, because our sample standard deviation was pretty close, not exact to the population standard deviation, right? So we expect it to be close. But here's what I mean whenever I say like the t-distribution is kind of crappy. Notice that there's not just one t-distribution, but every time I change my sample size, I get a different t-distribution, right? Like as many different sample sizes as there are, you get a different t-distribution. So if I want a standard normal distribution table, then I've done it. I've printed it off for you. You can do the CDF for the normal distribution based on that. But if I wanted to create a CDF table for the t-distribution, the problem is I would have to create, 100, 200 different pages that have a t-distribution for a sample size of 2, and a sample size of 3, and a sample size of 4, and a sample size of 5, and a sample size of 6. And every single one of those distributions is going to get a different CDF table. And I can't print off 100 different pages for all 22 students. You don't give me that kind of budget. Plus, you don't want to look through 100 different pages anyways. So it's